So this last unit, we looked at factoring polynomials. Now we're going to take it a step further and solve polynomial equations. So what does it mean to solve an equation? So when we want to solve an equation, we just want to determine values that will satisfy the equation where the right-hand side is equal to the left-hand side, or left-hand side is equal to right-hand side. So they're equal. So what are some strategies that we can use to solve polynomial equations? So we can use factoring or algebraic, just like we've been doing previously in this course. So one method solving algebraically would incorporate factoring, determining your zeros, any algebraic manipulations that you need to make. The other way is graphing your functions and then seeing where your functions intersect. And so your point of intersections would be your solutions. So let's do an example. We just want to solve this algebraically. So we have 4x cubed minus 12x squared minus x is equal to negative 3. So first thing, we want to bring everything to one side. So we have 4x cubed minus 12x squared minus x plus 3 is equal to 0. Now, if you notice, you can factor by grouping, so you don't need to find a factor and use long division if you don't want to for this case, because if you notice, there's a factor of 4, there's a difference of factor of 4 there too. And so we can factor by grouping here. So if we do that, let's factor a 4x from the first two terms, and we're left with x minus 3. And then we can factor a negative 1 from here, and then we're left with x minus 3. Okay, and then now, sorry, this is squared. If we factor out 4x squared minus 1, we're left with x minus 3 is equal to 0. And then this is a difference of squares. So it would be 2x minus 1, 2x plus 1 times x minus 3. So makes sense, it's a cubic function, and we have 3 roots. So now setting them each to 0, we get x is equal to half here, negative half for the second term, and 3 for the third. So those are our solutions. Those are also our roots and x-intercepts since we set the function equal to 0. So let's compare this to our graphical solution. So here our red equation, which is y is equal to 4x cubed minus 12x squared minus x, is just the left-hand side from our previous example. And then y equals negative 3 is just the right-hand side. So if we just look at it that way, we're just going to look at it from that perspective, we want to see where those graphs meet. So looking at the red function and where it meets the blue function, be right here. And that point is negative half. And that makes sense because that's one of our solutions. And then if we look at the other point of intersection, it'd be right here, which is half. Our last point of intersection would be right here, which is 3. Now for the green function, we just brought everything over to one side. So we're making it equal to 0. So where it has to intersect would be the x-axis. So that point would be right here, which is negative half as well, here, and here, which are our roots or intercepts when we originally found them in the previous equation. Okay, so let's look at our second example. The 2 paths of orcas playing in the ocean were recorded by some more oceanographers. The first orca's path could be modeled by the equation, let's call this h1t, is equal to 2t to the power of 4 minus 17t cubed plus 27t squared minus 252t plus 232. And the second by, let's call this h2t, which is 20t cubed minus blah, 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 where h is the height above or below the water surface in centimeters, and t is the time during the first 8 seconds of play. Over this 8-second period, at what time were the two orcas at the same height or depth? So first step is if we want to find where their positions are the same, we want to make their heights equal. So let's set h1 equal to h2. So basically we're finding their point of intersection. Okay, so let's expand this. Okay, so now I'm just going to bring everything over to the left and set it to 0, and I'm going to collect like terms in one step. So we got 2t to the power of 4 minus 37t cubed, that's just negative 17 t cubed minus 20t cubed plus 227 t squared minus 552t. So again, I'm just collecting like terms, plus 432 is equal to 0. Okay, now we have to use the factor theorem to figure out what will make this 0. So I'll just tell you. If you plug in 4, you'll get 0. So we know that x minus 4 is a factor. Okay, so now we need to long divide. So setting this up, we have x minus 4 here, and then 2t to the power of 4 minus 37. Okay, so let's go ahead and long divide this. So we're still not done. We still need to factor this top expression right here. So since it's a cubic function, we probably need to use the factor theorem. So let's do that. Okay, so if you plug in, I'll just tell you, if it's f of 9, will give you 0. So therefore, t minus 9, sorry, I used x above here, but it should be t. So t minus 9 is a factor of this above expression here. So let's go ahead and long divide it. So this is what we get when we long divide. And so our factors are going to be t minus 9, t minus 4 from before, and 2t squared minus 11t plus 12. Okay, so I just rewrote this up here. That's from the page above. And now we wanted to take this trinomial and factor it further. So what I did is take two numbers that multiply to 24, so from the 2 to the 12, and add up to negative 11, which are negative 8 and negative 3. So we're splitting up that middle term as negative 8 and negative 3. Then I'm common factoring these first two terms, so pulling out a 2t, and then we have t minus 4 left over. And then here I can factor out a negative 3, and we get t minus 4 left over here. So our final expression here is t minus 9, t minus 4, 2t minus 3, and t minus 4. Okay, let's clean it up. So t minus 9. I'll bring the t minus 4's together, so it's squared, and 2t minus 3. Okay, so now let's determine our roots. So here we have t is equal to 9. Here t is equal to 4. And then here, t is equal to 3 over 2. So we can reject this answer right here because it's out of the range. It's not in the domain. This works, and this works as well. So therefore, they meet at 4 seconds and at 1.5 or 3 over 2 seconds. Okay, so now let's verify the solution graphically. So this is the right-hand side of the equation, or the way we called it earlier was h1t. The blue is your h2t. So let's just look at that. So h1t, which is your red, it's this function. Your blue one is h2t, which is your blue. And we want to find our points of intersection, so when they're equal to one another. So we have one here. And that looks like it is 3 over 2. And we have one here at 4. And we have another one right up here. And that looks like it's 9. And even though it's out of the range, it's still a point of intersection. Okay, so now let's just look at this green function over here. That's when we brought everything to the left, so we set it equal to 0. So now we're looking for the x-intercepts. So our x-intercepts for our green function, we have one here, which is at 3 over 2. We have one right here at 4, and right here at 9. Okay, let's look at this next example. So we have x to the power of 4 plus 5x squared is equal to -1. So again, we want to maybe solve it algebraically and then look at it graphically. So if I am going to use the factor theorem, I'm going to try to find a function that, or a number that will make this whole thing equal 0. So we can bring everything to one side. So x to the power of 4 plus 5x squared plus 1. It's a cool color. And if we try to find something that makes this equal to 0, we can't. So there are no solutions here. Okay, let's look at what's happening graphically. So here is your left-hand side of that original function, and here's your right-hand side. So we're trying to figure out where the red function will intersect the blue function. And because they never intersect, there are no solutions. Then we took the green function, set it equal to 0, so we brought everything to the left. And I guess we're trying to look for our x-intercepts here because we're equating it to 0. And that's here. It doesn't cross the x-axis, so therefore no solutions. So we can see how that works graphically. So because it never intersects, it doesn't have any solutions. Okay, so here's another interesting case. If we have x cubed minus 2x plus 3 is equal to 0, but I'm trying to use the factor theorem to find something that'll make this equal to 0, like a number that will make it equal to 0, so I can use the factor theorem. I can't find any whole number that will do that. So in this situation, you cannot use the factor theorem to factor. Okay, so let's see what's happening graphically. Okay, looking at it graphically, our red function is the function, blue is the x-axis, and we want to figure out where they intersect. So if you notice, at this point, it's actually x is equal to -1.89. So since that's a decimal, there was no way we were going to guess that number to make this equal to 0. So there was really no way to factor it. So in this situation, we would have to use a graphical solution to solve this. Okay, so to summarize, we looked at two different ways to solve these kind of polynomial equations. First, we would try to factor using the factor theorem. If that didn't work, then we would look at it graphically. So if an algebraic solution exists, we can use that. And so if we can factor it, we would factor it. If there's no solution, we would solve it graphically. Or if factor is not easy to find, such as if it's a decimal or a fraction. There you go.